Alright, so let's start this session. Okay, so uh, we talk about the number and SNR increase with respect to the accuracy. So we see that we like to have higher SNR, or in other words, in other terms, we like to have the number of observations to be large. For example, a large N. Okay, so now uh, we have some numerical verifications for these figures. Okay, so now let me see. Now let's turn to MLE, MLE for transformed parameters. In many instances, we wish to estimate a function of theta, the parameter characterizing the PDF, a function of theta instead of just theta. So for example, we may be interested in the value of DC label in WGN, but only in the power a square. In such a situation, the MLE of a square is easily found from the MLE of a. Some examples illustrate how this is done. So let's first take a look at the example. Transformed DC label in WGN. Consider a data xn equal to a plus w, where w is WGN with variance sigma square. We wish to find the MLE of phi of alpha equal to exponent of a. The PDF is given by this. Notice that although we are interested in exponent of a, it's not going to change the original data model, and therefore the PDF is not going to change, right? So you cannot say, hey, I'm interested in exponent A, so can I put exponent A in here? The answer is no, because this comes from the data model. That data model doesn't change just because you want to have something different, right? It determines determined by the physics of your observation, the physical system of your observation. So even if you're interested in exponent of A, it doesn't change the data model. As a result, it doesn't change the PDF, right? So you have P of XA equal to this, equal to this, and then it's parameterized by the parameter theta equal to A. However, since alpha is a one-to-one transformation of A, we can equivalently parameterize the PDF as this one. So if you want to say it's this one, what have we done here? We have done taking, be careful, let's take a look at this. You take a natural log here, you get A equal to ln alpha. Then you put ln alpha into this position, you get ln alpha here. Okay? So you get this, and you to change your variable, you get ln alpha here. Where the subscript indicates the PDF is parameterized according to a transform parameter. So now we have x equal to ln alpha plus this. And they are equivalent. So the MLE is alpha is found by maximizing over alpha. Setting the derivative of p with respect to alpha equals 0 yields this. This is what? This is again chain rule. Chain rule, and then change your variable. You get this. Ln alpha divided by alpha is equal to 1 over alpha. Okay, this is a calculus identity. 微积分的恒等式哦，微积分恒等式，不熟悉的可以再稍微复习一下微积分哈。Okay, but x bar is just the MLE of A, so alpha hat is exponent of A hat equal to exponent of theta hat. The MLE of the transform parameter is found by substituting the MLE of the original parameter into transformation. This property of MLE is termed the invariance property. So what that means is you have alpha hat is bounded x bar, but x bar is the MLE of A, right? So alpha hat is bounded of A hat. So what that means is it has this invariance property. Invariance property meaning that if you have a MLE for A, it's a function of we want to be interested in a function of A, you just take the function of the original MLE, then you get the new MLE. The function, the MLE of the function of alpha, okay, of A. So that's what it means here. Okay. So now we talk about the invariance property of MLE. The MLE of the parameter alpha equal to g of theta, where the PDF p of x theta is parameterized by theta is given by alpha hat equal to g theta hat, where theta hat is the MLE of theta. The MLE is obtained by maximizing this. Of course, this is what we did before. If g is a non-one-to-one function, then alpha maximizes the modified log likelihood function Ptx alpha, defined as this. So we will complete our discussion by giving another example. We're interested in power of WGN. We observe n samples of WGN with various sigma square, whose power in dB is to determine. To do so, we first find MLE of sigma square. Then we use the invariance principle to find the power P in dB, which is defined as P equal to 10 log 10 sigma squared. The PDF is given by this, right? We're interested in this rather than the original DC label. Okay, so PDF is given by this. Then we differentiate the log likelihood function. You take the log, but notice that this is no longer DC label. This is sigma square, and then you differentiate it by sigma square and do some calculation. You get this as the outcome. Okay, so eventually you set it to 0. It yields MLE for this, and then the MLE of the power in dB readily follows as 10 over this and 10 log this. Okay, so again it again verifies if we are interested in power in dB. Power in dB is actually a function of the power, right? You take the 10 log something, that it is to transform the power into power in dB. Okay, it's still power. Its name is still power, but its unit becomes dB. So again, we will see that you take log 10, you get 10 log 10 of the original estimator. Recall that this is the original estimator. Okay. And then the other thing is numerical determination of the MLE. A distinct advantage of the MLE is that we can always find it for a given data set numerically. This is because the MLE is determined as the maximum of a known function, namely the likelihood function. If, for example, the allowable values of theta lie in the interval, then we only need to maximize this over the interval. Then we do a grid search. Grid search 就是我常常讲到的数值方法的其中一种方法。好，你有很多方法， 你可以用二切法 Gray Search， 或者是多维度的 Gray Search 也是可以的。有各式各样的方法。其实，在做 machine learning 就是在做一个 multiple variable 的 optimization 的问题啊，只是说它是用 data training 的方式来做。可是事实上，这个所谓的 optimization 这件事情或 numerical approach， 这个是已经发展了应该是有20年以上的一些数学领域的知识了哈，就是会用到。如果有同学有兴趣，应该可以稍微学一下哈。So this is a great search over this, and then of course the question is how many grades are you going to put? You can put 10, 100, 1,000, 10,000, a million, right? A small number of grades you put, you get better accuracy. Okay, I think that's trivial. All right, so let's take a look at the example. Exponential in WGN. We consider the data model. This data model is different from previous one where we have A here. And now it becomes R to the N here. So you get an increase with the R, right? Not always increase, but it's R to the power of something, R 的几次方的这种形式啊哈。The parameter R exponential factor is to be estimated. Allowable values are R larger than 0. The MLE of R is a value that maximizes the likelihood function. Okay, this is standard PDF written out, and then think of it as a function of R, then it becomes likelihood function. Okay, so likelihood function, then you want to find a thing that minimize this. Then this is the, this one doesn't matter. This one doesn't matter. The remaining term is this. So you put it here. You do a differentiation and set it to 0. You produce this. Okay. So up to this point, at least we are happy. We are happy because we get a closed form solution for the MLE. But let's take a look at it carefully. This is not a nonlinear equation for R. Cannot be solved directly. So we will now consider the iterative methods of Newton-Raphson. OK， 所以我们就开始用一些数值方法。Newton-Raphson 就是一个数值方法。可是事实上，你知道吗？数值方法在过去20年里面演进很多。Newton-Raphson 其实是算是比较老旧的一个方法了，但是可以用。只是说你如果随便摄取一下、找一下或数值方法的课本来看一下，你会发现大概有5种方法、10种方法可以解这个问题。Okay, so it doesn't matter. Let's just follow the process and see what happens. So you take the partial derivative equal to 0 and you get a g, and then g is equal to this. This is what? This is again what I say first order Taylor expansion. 这是 Taylor expansion 的一阶近式啊，对不对？泰勒展开式的一阶近式。你也可以说你想要2阶啊，2阶准了一点吧，3阶更准，4阶更准，只是更复杂而已。OK。So you do this Taylor expansion and approximation, you get that, and eventually you get this. So you get a theta k equal to this iteratively. So you put in the initial number, it gives you a new number. You put in the initial number, it gives you a new number. Eventually, it's going to approach that optimal solution. Okay, but again, 数值方法是没有保证的哈，没有保证 global optima， 没有保证会 converge， 所以通常会有一些调整的技巧了哈。有一些时候是，比如说你做了超过1000步就停，或者是每一次要跳步的时候乘以 0.9， 让它的步伐越来越小，到最后会 converge。我想用数值方法，同学应该会有印象。好的一些技巧 ，but it doesn't matter. Okay, it doesn't matter. It's just there are many heuristics heuristic adjustments in the approach. Okay, eventually you are going to reach that optimal point, hopefully. But if not, then what? 如果没有达到我们想要的高光体嘛，那怎么样？那就没办法。哦，这数值方法就是因为你没有 close form 所以才做的。啊，如果数值方法解到最后没有办法到 global t 那这个也是没办法的事情了。好，这数学是有极限的。Okay, so that's about what we are talking about in this chapter, and then there will be extension to a parameter, to a vector form. So, MLE is found for this, but this is what it's a vector form. Okay, it's a vector form. So let's take a look at one example. You have DC label and sigma square. So you do it partial with respect to A, partial with respect to sigma square. Then you set it to 0, you get this. You set it to the first one to 0, you get this. The second one to 0, you get this. So the MLE is X bar, and then this. So this is for A, this is for sigma square. Okay, so formally, asymptotics of the MLE in vector form is if the PDF of Px theta of the data satisfies the regularity condition. Again, the regularity we talk about many times. Then the MLE of the unknown parameter is asymptotically distributed according to this theta distributed by this, where I theta is a feature information matrix evaluated as a true value of unknown parameter. So mostly this will be the formal definition for the MLE, formal definition of MLE. But we consider previous example, we get something like this, right? We get X bar distributed by A sigma square N, and then P 记得吗？哈，我们有这个 X over 这个 statistic，这个 statistic 是 chi-square to the degree of n minus one 的哈。Okay, so for large n, it's well known from central limit theorem. Central limit theorem 的其中一个解读就是，当资料量够大的时候，这个有很多 interpretation 啊，其中一个就是，当资料量够大的时候，会趋近高悬这样子。Okay, so chi-square approach is Gaussian. Then of course you get this distribution. So you have a sigma square equal to that. Sigma square equal to that. So you expect of theta hat equal to A and equal to this. This is what? This is supposedly biased. Then it becomes unbiased. A sigma square equal to theta. Okay, and C of this is feature information. You do the feature information derivative partial A, partial sigma square, you get this. And then you do the inverse, you get this. And this is what? This is, let's see. You see here. This is the Gaussian distribution feature information thing, right? 我们再回到这里 you get this, right? This is page 167, you get this. 所以你要算 theta 跟 feature information, 然后再 take inverse, okay? So now we are doing it here. We are doing it at this. We're doing it here, so you get feature information inverse. Okay. So I think the next thing is invariance property of MLE. the MLE of the parameter alpha equal to g of theta, where g is the r-dimensional function and of the p by 1 parameter theta. So PDF is parameterized by theta is given by alpha hat equal to this. For theta hat, the MLE of theta, if g is not invertible function, then alpha maximizes the modified log likelihood defined as this. Okay. So what that means is if we have a transform of the parameter theta, then the optimal solution means MLE. Okay, the MLE for theta, take the function of g, it will give you the MLE for alpha hat. Okay, that's called invariance. Invariance 叫做在转换的过程里面不变性的不改变的特性，这个叫做 invariance 啊，不改变的特性。Okay, if you get a MLE for theta, you take the function, you get MLE of alpha hat. Okay, as simple as that. Okay, then there will be some derivations and examples, and I recommend you to take a look at those examples. Okay, so I think up to here, that will be the end of this session. We'll continue next day. Thank you.